The sun is the source of all life on Earth. Without the sun, there would be no Earth's ecosystem. Let's imagine if the sun were to disappear, the Earth would undoubtedly lose its life. But how did this mother of life, sun, come into existence? Did it simply appear when it was said, "Let there be light"? Now, let's find out how the sun was born. Gases and dust floating in the universe are known as interstellar matter. Interstellar matter is typically composed of 99% gas particles and 1% dust. This gas is composed of approximately 90% hydrogen, 10% helium, and trace amounts of heavier elements. When these interstellar materials accumulate into a giant cloud through gravitational contraction, it's called a nebula. Stars are born from this interstellar matter. As the interstellar materials gather and increase the density of the nebula begins to collapse under its own gravity. The nebula contracts into a sphere and the density in the center increases. As the density continues to increase, the gravity also grows stronger and the contraction continues. Because the density is so high, the atoms collide with each other. Gravitational energy converts to heat, and the temperature at the center of the nebula rises. The nebula then finds a balance between two forces: the gravity that seeks to shrink towards the central core, and the energy that attempts to spring outward due to gas pressure and rotation. Finally, these two forces reach equilibrium, causing gravitational contraction to cease without any expansion occurring. Now the nebula has been born as a protostar, a luminous globe with high density and temperature. Although the protostar is born, it does not stop growing. The center of the protostar contracts and expands repeatedly, continuously consuming surrounding interstellar matter. The mass of the protostar gradually increases, and so does the temperature and density. The hot temperature in the center of the protostar is transferred to the outside through convection, and the protostar slowly begins to brighten. This process continues. Then, at one point, something astonishing happens. When the internal temperature of the protostar reaches 10 million degrees Celsius, which is about 18 million degrees Fahrenheit, nuclear fusion reactions begin in the central core. A star that shines on its own like the sun has just been born. A star that burns hydrogen through nuclear fusion like the sun is called a main sequence star. Let's take a close look at the nuclear fusion process of this main sequence star. Firstly, nuclear fusion is a reaction where atomic nuclei combine to form a heavier nucleus. In order for nuclear fusion to occur, the temperature and pressure must be sufficient. If the temperature and pressure are low and the energy is also low, the electromagnetic repulsion between atomic nuclei prevents the atoms from coming together. It's similar to how the same poles of a magnet will never stick together no matter how hard you try. Atomic nuclei generally cannot combine under normal conditions. For protostars with low temperature, density and pressure, nuclear fusion won't occur no matter how much hydrogen accumulates in the center. On the other hand, if conditions of extremely high temperature and pressure are created, like in the core of the sun, the distance between atomic nuclei narrows. When the distance between atomic nuclei is sufficiently close, neutrons operate a force known as the nuclear force, which links together atomic nuclei. In doing so, atomic nuclei are enabled to bind together. In the center of a star, 4 hydrogen atoms undergo nuclear fusion to create a single helium atom. During this process, about 0.7% of the mass disappears, and in accordance with the principle of mass-energy equivalence, this 0.7% of mass is emitted outward as energy forms such as light and heat. This nuclear fusion reaction in the star's core gives birth to photons. It takes these photons million years to reach the outer surface. The sunlight that reaches us is actually the result of light that has traveled from the sun's core for over 1 million years before finally escaping. When we look up at the night sky, we see the stars. These stars are lights from nuclear fusion happening somewhere in the universe. The sun burns about 400 to 600 million tons of hydrogen per second, and the helium born from burning this hydrogen accumulates in the center of the sun. Once a protostar starts a nuclear fusion reaction, gravitational contraction stops. Nuclear fusion occurs in the high-pressure environment at the center of a star, and energy is released. This energy is then heavily suppressed by the enormous gravity of the star. This balance of nuclear and gravitational forces stabilizes the entire star. The star then continues its endless nuclear fusion without increasing or decreasing in size. Our Sun has maintained this state of energy balance for approximately 5 billion years. Although 5 billion years may seem like an eternity from a human perspective, from a star's perspective, this is just entering its youthful stage. This main sequence stage occupies the longest time in a star's life. Let's take a look at the Sun as a young main sequence star. The baby Sun had about 80% of the current luminosity, but over the course of 5 billion years, it gradually brightened to its current state. The Sun will remain in the main sequence stage for another 6.3 billion years, continuously heating and brightening. About 700 million to 900 million years from now, the energy radiated by the Sun will increase too much, raising the Earth's temperature, and nearly all life forms on Earth will disappear. In the center of the Sun, nuclear fusion reactions continue to occur, but the hydrogen that the Sun can burn is decreasing day by day, and the product of nuclear fusion, helium, is increasing. As helium increases, the average molecular weight increases, and the central nucleus slowly contracts under that pressure, increasing density and temperature. As the internal temperature of the star rises, the surface energy continues to grow and the luminosity of the star increases. The Sun maintains the main sequence stage for a relatively long time. However, the period that triggers nuclear fusion is determined by the birth of the star. Relatively low-mass stars emit weak energy over a long period and therefore stay in the main sequence stage for a long time. On the contrary, if the mass is larger, a tremendous amount of energy is radiated in a short time, so the energy is exhausted quickly and the star evolves to the next stage. Stars either burn brightly but briefly, or faintly and enduringly. There's no in-between. It's a relief if they can become a main sequence star. Not all nebulae or protostars in the universe enter this main sequence stage. Celestial bodies possessing about 1/12 of the solar mass, significantly smaller than the Sun, are unable to reach the necessary temperature and density to initiate hydrogen nuclear fusion. Instead, they gradually exhaust their lifespan by slowly consuming deuterium or lithium, ultimately becoming brown dwarfs. If Jupiter had a much more abundant mass than it is now, it might have undergone nuclear fusion. That means our solar system almost had 2 stars, meaning our galaxy would have been a binary system. But becoming a star in the sky is not easy. But there's something curious. What happens when the Sun burns all its hydrogen? What will the Sun, now devoid of hydrogen and only full of helium, transform into? Just like a car stops when it runs out of fuel, will our sun stop as well? Next time, we will look into the sun's next evolutionary stage, the red giant stage. Tune in next time as we continue our voyage into the red giant's fiery embrace.